Okay, so in the last lecture we studied on statically admissible stress field. Okay, and today we have a lot of very important topic on stresses. So first one, let me think about stress on a material surface. Yeah, let's think about some body here. I'm gonna cut this body with some arbitrary plane. Okay, and here this is my material point, and this surface have a normal vector n. And this surface we can calculate traction. So T equal stress n, right? We already know about this equation. So T will be, let's say this is T, traction on the surface. This traction in the surface is changing depending on the n, vector n, which is a vector normal to this surface, right? And this traction vector can be decomposed by two parts. One is a normal part. So this one, let's say this is a sigma n. And its direction is same to the n. The other is a tau n, tangential component. So T can be written by normal component plus tangential component, right? We can decompose it. This is just simple vector operation. So sigma is a normal component. Tau is a tangential component. So here the question is that how to find that normal component and tangential component. So let's look at this equation only. N equals stress N plus tau T. Let's multiply N transpose. Then we can have N transpose stress N plus N transpose tau T, right? Then what we can have? Here, left hand side, N transpose stress N equal just sigma. We can have only normal component because the N transpose N equal 1 and transpose T equal 0. Because N and T is normal to each other and both are unit vector. So similarly, we can also calculate the tangential component. So T transpose stress N equal tau. So we can calculate the tangential and normal component. Here, if the stress is bigger than 0, normal stress, we are saying this is tension. This is smaller than 0, compression. So in vector diagram here, this is tau, and this is t. This is t and tau t. So size of t equal size of t equal square plus tau square, right? Or tau will be t minus square. So we can calculate also tangential component. So we are saying this is a shear component also. Tangential or shear. Shear stress component can be calculated by this equation here. And square, here I need to have square, and square. So now you know how to decompose the traction on a material surface. We can decompose that traction in two parts, normal part and shear part. Okay? Then we can also calculate the magnitude of a normal part and magnitude of a shear part. This is just Pythagoras theorem, right? Okay, then let me give you some example. Okay, I like give example. Let's say we have a stress vector, stress tensor 10, 0, 2, minus 1, minus 1, 0, 0. Let's say we have a stress. And we have a direction n, 1 square root 2, 1, 1, 0. Then you can calculate the sigma and tau, right? With that equation. Very simply. Okay. I believe you can find that those two components without any help. So, next topic we need to know is the principal stress. You know what's the principal stress? 정호, can you explain the principal stress? Can you explain? What's the principal stress? Huh? Maximum? Minimum?
It's a position without any shear stress.
Right.
And only axial stress.
Okay, so we have a material surface here and its normal vector is n. So if we changing the n direction, this direction is also changed, right? And its normal component and tangential component. Here the sigma and tau will be changed. If we change the angle by changing the vector n, right? But for a certain n, this is shear become 0. So there is only normal stress. It means this direction of traction is same to the n. So at some direction n, okay, the t vector, traction vector, is something like this. So t become just some normal. We can have this kind of situation. Actually, tau t, this is 0. Okay? So we have only normal stress. Let's say n. So the condition for this is like this, and this is condition. So we can write down stress vector, stress tensor, and n. This is condition. When we have only normal stress, it means shear part is 0. Shear stress is 0. Have you ever seen this kind of this shape of equation? Sigma is matrix, some vector, same vector here, and this is scalar. Watch this. This is eigenvalue problem, right? Eigenvalue problem. So if we solve the eigenvalue problem, we can find the direction, this direction, and the corresponding stress. So this is eigenvalue problem. If we solve this eigenvalue problem, we can find eigenvalue because the stress tensor is a 3 by 3 matrix. We can find 3 eigenvalue, and that 3 eigenvalue become a principal stress. Stress 1, 2, stress 3. And usually we can have a principal stress. And also we can find eigen vector. N1, N2, N3. These are principal stress direction. So in 3D, if we solve in 3D or 2D, if we solve this eigenvalue problem, we can find out principal stress and principal stress direction. So if we put that principal stress direction in this equation, so in this equation, you will find only normal stress. Okay, shear stress becomes 0. So in 3D, in general, we have 3 principal stress direction and 3 principal stress. Okay? Okay, so let me give you example. Example. Yeah, let's consider only simple 2D problem. So usually the eigenvalue problem looks like this, and to solve this eigenvalue problem, we need to make this equation like I n, right? Then how can I solve this? So this equation has a solution only if determinant equals 0. This is named Cramer's rule. So if you take the determinant of this matrix, we can have a polynomial characteristic polynomial. So P sigma will be a determinant minus sigma I. This is a characteristic polynomial. So if we solve the characteristic polynomial, we can find the eigenvalue, right? Okay, so let's consider only 2D case. Stress is -1, 2, 2, 2. Okay, this 2D problem. Then we need to solve the let's make minus sigma I become -1 minus sigma 2 minus sigma, right? So at only for the diagonal component, we subtract the sigma. And what's the determinant of this? So characteristic polynomial become, you know how to calculate determinant. It's simple. So -1 minus 2 minus sigma minus 4. And this is -6. Okay, so solution of this, we need to solution. We have a solution. Eigenvalue 1 equals 3, 2 equal -2. This is eigenvalue. To make a characteristic polynomial become 0. Right? In 3D case, this characteristic polynomial will have a cubic function. So in general case, it's very hard to find the sigma which make a characteristic polynomial make 0, right? Then we need to use some numerical method, some searching method like bisection method or Newton-Raphson method, right? Then we can find the root. Okay, so now we found the eigenvalue, which become principal stresses. And next, how we can find the direction. Principal. So we need to eigenvector. So eigenvector. Okay, so let's consider the case, second case, -2. Let's put this equation into this one here. Then -1 sigma minus 2 2 minus 2, okay, n, okay, I need to put the 2 here, 2, 1, 2, 1, and 2, 2 equal 0, 0. So 1, 2, 2, 4, and 1, 2, and 2, 2. What's N1, N2 here? So let's look at this equation and this equation. This is we have a two linear equation, but same equation, right? If you take this is independent system, right? So how can I make 0? So we can only determine the ratio. If N1 equal -2, N2, 1, then we have 0, 0, right? Or N1 equal 2, N2 is a -1, then we can also. So N with 2 become after normalizing the vector 2 minus 1, something like this. If you put this in that equation, you will have 0. And square root 5 is used to normalize, okay, to make a unit vector. And similarly, we can calculate N1 with a principal stress 1. Then it becomes 1, 2. So let's look at this. If you take the dot product of these two vectors, what happens? You take dot product 2, 1, 1, 2, 0, right? So N1, N2, 0, right? How about the N1? N1, N1, 1, N2, N2, 1. So principal directions are normal to each other. Okay, orthogonal. It means this principal stress direction can make some Cartesian coordinate system. It can be a base vector of a Cartesian coordinate system, right? Understand? Because they are normal to each other and they are unit vector. Okay, and okay, so if you put this direction into the original equation, you will have only normal stress component. Okay, you need to check it. Okay, so next concept. This is concept is a little bit complicated maybe. So usually when we define the stress, we need to first define the coordinate system. So this is Cartesian coordinate system. So in Cartesian coordinate system, we define the stress, right? So in tensor form, Eij, Ei, tensor product EJ, right? So after finding the principal structure direction N1, N2, N3, we can define another coordinate system. Okay? Something like this. This is also Cartesian coordinate system, but different from the we defined previously. So we can write down the stress in this new coordinate system. So we are saying that coordinate system is this. Okay, so then this stress become 1, E1, sorry, N1 plus N2 plus so we can write down stress tensor with that principal stress and principal stress direction. So base vector is changed from E to N. Then in this principal new coordinate system, we have only diagonal component, no shear component. Because we changed the coordinate system to principal stress direction. So this is a little bit hard to understand maybe for you. So this is a coordinate system defined by so for example, okay, in 2D, stress was -1, 2, 2, 2. In the coordinate system, E1, E2, E3, right? How about stress? Become let's see, 3 minus 2, 0, 0 in coordinate system defined by base vector and okay, I don't need to use this 1 and 2. Right? So if we change the, you already know that if we change the coordinate system, the component will be changed. Component of vector, component of matrix will be changed, right? So component is changed because we changed the coordinate system. But physical quantity is exactly the same. Nothing change. Physical quantity doesn't change. Even we change the component and base vector. So if you put this into this equation, you can have exactly the same matrix in left-hand side and right-hand side. Okay? So we can define the coordinate system by principal stress direction. And principal stress direction, we have only 3 normal stress, right? Stress 1, 2, 3. Sigma 1, sigma 2, 3. This stress 1, 2, 3 is something like a position in the space, right? Position in the space. Position in the space can be defined by 3 value, right? So, similarly, so because of that, we are saying this is a principal stress space. It's not an actual space, but because we have only 3 value, so we can think like a space. So all the stress situation can be defined by 3 value in its principal stress space. Okay? Okay, this is okay. So we need to here principal stress space is a sigma 1, 2, 3. This is a principal stress space. So it's something like this. Here, and 1, and 2, and 3. We can put some point somewhere. This is principal stress space defined by 3 principal stress value. Any question? So today you need to understand a lot of different concepts. So but it looks a little bit complicated, but once you understand, this is nothing. Any question? Okay. Hydrostatic pressure. This is some special stress state. Okay, hydrostatic pressure. What's the hydrostatic pressure? Hydro means water, right? Static means no motion. So when some subject, some body is in the water, is subjected to the hydrostatic pressure, right? So for example, this is water And here we have some subject. It has a pressure P, or what's the characteristic of a hydrostatic pressure? It's applied to the surface, and its direction is always normal, right? So hydrostatic pressure is applied to the normal direction. So hydrostatic pressure doesn't have any shear component. It's always normal. There is only normal stress, right? So hydrostatic pressure can be expressed by minus P and I. P is a magnitude of pressure, I is an identity matrix. So it becomes minus P, minus P, minus P, and other components are 0. Right? So in the state of hydrostatic pressure, there is already only normal component, right? No shear. So it means these three are principal stress. So here, principal stress 1, 2, 3 are same to minus P. So T and equal stress and equal minus Pn. So in principal stress direction, principal stress of hydrostatic pressure state has all the same principal stress. Principal stress 1, 2, 3 are the same, and its value is minus P. Then what's the direction? What's the direction? Huh? All the direction is principal stress direction. Okay? All the direction. So it means the hydrostatic pressure is independent of direction. Independent. Hydrostatic pressure state is independent of direction because for all the direction we have a same normal stress and no shear. Okay, so this is a very special case of stress. Okay, fluid mechanics we are using this concept. Okay. Okay, stress invariant. Stress invariant is a scalar quantity. functional the stress component So stress invariant is a scalar quantity, okay? Expressed as a function of stress component. So stress 1, 1, 2, 2, 1, 3, 3, 3. These are stress components. So with these stress components, we can make some function. Okay? It's a function which does not change regardless of base vector of the coordinate system. So when we make some function, which is based on the component of stress, okay, that function, value of function doesn't change when it changes the coordinate system. Then we can say this is stress invariant. Invariant means no change, okay? Something which doesn't change. That's invariant. So variant means changing. So various and varying, it means changing. In means not. So not changing. So there are some value which does not change. So for example, so stress was -1, 2, 2, 2, and become in K 3 minus 2, 0, 0. In E1, E2, in N1, N2. So we already know the component of stress is changing. When we change the coordinate system here, this is a coordinate system, is changed. And component also changed. -1 become 3, 2 become 0, 2 become 0, 2 become -3, right? But let's consider sigma 1, 1 plus sigma 2, 2. Here, sigma 1, 1 plus sigma 2, 2. What's this? 1. Here, 1. Doesn't change, right? This is invariant. So this is, say this is some function, ij, right? Doesn't change, right? This is stress invariant. Amazing, right? Okay, and actually we have 3 stress invariant. Okay, that's the one of them. So we are saying that's I1. First one is I1. Trace stress. Trace mean only some or diagonal component. Okay, so we are only summing the diagonal component. So it means 1, 1, 2, 2, 3, 3. Okay? In tensor form, I. This is I1. Stress environment, first stress environment. And I2 is a trace stress. We are scaling. We scale the stress and take the each sum of the diagonal component. 1 over 2. Sorry. I need to have a 1 over 2 here. I2. 1 over 2. Stress Ij. Ji. I3. Ki. Okay. So we have 3 stress environment. If you want, you can check it. Okay. So we have a 3 stress environment. So example. In the higher stress pressure, stress become minus P, minus P, minus P. So you can find I1, I2, I3. Right? This is a very simple problem, so we can very easily calculate minus 3p, 3 to p square minus p cubic. So that I1, I2, I3 never change. Even you change the coordinate system, Cartesian coordinate system. Okay? Direction of Cartesian coordinate. Okay, then, okay, so here we need to understand one of the important concept. Note. You know the meaning of isotropic. Isotropic means material property doesn't change. Okay? Depending on direction. it means material property doesn't change even we are changing the coordinate system, direction of coordinate system. Okay? So, note the behavior of the isotropic material can be described in terms of stress invariant. Stress invariant I1, I2, I3. So, if there is just some property of isotropic material, okay, that is a function of I1, I2, I3. Because only I1, I2, I3 is a stress environment. Doesn't change depending on direction, right? Okay, any question? So, a lot of concepts I introduced today. Okay, so stress deviator. This is stress. S. It can be decomposed by two parts. S plus M I. Okay. Here, sigma m equal I1 over 3. So 1 over 3, 1, 1, 2, 2, 3, 3. Right? This is the mean normal stress. So we are saying here sigma m equal mean stress or volume stress. So stress decomposed by two parts, deviator part, and this is a volume part. Or hydrostatic part. So deviator part can be calculated by like this, I. So volume part has a shape of hydrostatic pressure, right? So in the stress, if we subtract hydrostatic pressure, okay, there only remain deviator part. And why the name is the volume part? Because the hydrostatic part produce change of the volume. So we are saying that's the volume part. Deviate part doesn't make a change of volume. So you're gonna know why that's important when we study about the strength of material. Maybe next week. And also, we have an invariant or deviate to stress as we are saying J1, J2, J3. This is a invariant. J1, J2, J3. These are also very important in when we studied strength. J1, J2, J3. So today we studied 6 invariant. I1, I2, I3, J1, J2, J3. Right? Okay, so actually I need to show you some wrong example, but I don't have time. Okay, any question?